Okay, before I get to the actual concept of completing the square, I want to work my way up to it. So the first little bit is kind of just a review. You guys have been working on functions recently. Functions are basically equations. And with equations, we can do things like graph them, give you an equation, give you a table of values. All of those things are interrelated. Okay. So far, we've really only focused on linear functions and quadratic functions. But this is really like the gateway section to most of Math 30. This is a really key unit for next year, where we're going to talk not just about linears and quadratics, but a whole list of functions here. And I'm sure there's more that I haven't even thought of. And they all pretty much follow the same concept. I'm going to show you what a graph looks like. I'm going to talk to you about how the equation works. And you have to be able to connect the graph, the equation, and a table of values together. And then probably you have to use it to solve some sort of problem. Because we don't just graph things. Usually the graph is part of like a diagram that's necessary in problem solving. Like, for example, us with quadratics, the typical quadratic graph might look like this, where there's a person diving off of a diving board, and this is them hitting the water. Does that make sense? So, here's some pictures of some of the graphs that you've learned so far. This one just happens to have one we're going to learn later next week. Next week, we're going to talk about what's called an absolute value graph. We've actually done absolute value in our first unit. What does absolute value mean? All of it's positive. If you have a positive number, it stays positive. If you have a negative number, it becomes positive. Well, one thing you might notice about this graph here, does it ever go down here in the negative section? This type of graph that we learn next week is actually very applicable to things like reflections. I like to do pool and imagine like a bank shot, where what happens is you shoot the pool ball, it hits the wall, and it banks back off again. So exponential is actually done next year in grade 12. Same thing with logarithms, cubics, tans, and sines. These are all just random graphs that at some point you'll learn about. But I want to focus mostly on quadratics because that's our section for right now. So here's a quick review of quadratics. Quadratics have this U-shaped parabola to them. And one of the key parts of the parabola is the vertex at the very, very bottom. And we often denote it as H and K. If we write it in vertex form, it's very easy in vertex form to tell you what the graph is going to look like. Let me just make up an example. Y equals -2, x minus 2 squared plus 7. You shouldn't need a graphing calculator to roughly know what this graph is going to look like. All I hear is loud. What's the -2 going to do to the graph? It'll be a frowny face, and the 2 is going to kind of make it a little more squished as opposed to like flattened out. The really important part is this 2-7 combo. On a grid right here, the -2 is actually like a +2. And so 2 and 7 is up here. So I should be able to tell you the graph is going to look roughly like that. Does that make sense? Vertex form, therefore, is a very useful format of writing a graph because we know where the vertex is. We know the tone of the graph, the character of the graph, the direction of the graph. That's probably the better way of putting it. The problem is, what happens if it's not written in vertex form? What other formats do we know? I think that's what my next slides are about. Well, let's just do this first, and then I'll get to that part. What kind of format is this? Is that vertex form? What do we call that form? A standard form is actually the term we use. Everything we've been doing is quadratic. This would be known as standard form. Why is standard form useful? Yeah, I know the y-intercept is 3. Does that help? I know it's upside down because of the -2, but there's one more reason why standard form is useful. The quadratic formula. Because what this right here means is take -2x squared minus 5x plus 3 and tell me where it equals 3. Well, if I want to solve this algebraically, I might subtract 3 from both sides. you'd get minus 2x squared minus 5x plus 0 equals 0. And I'm not going to solve this, but we would use the quadratic formula.
Miss Doc, please dial 103. Miss Doc.
That's what standard form is useful for. That's why I taught you guys standard form whenever we did quadratics. I'd always tell you, well, try to write this thing as though you can make it equal 0 on the other side. And then you can use that quadratic formula to get you your answers. Does that make sense? Likewise, if you did this, it would be minus 2x squared minus 5x plus 3. Make it equal to 8. This is standard form. Do you know where the vertex is? No. Do I know where the y-intercept is? Well, I guess it's 3. But the biggest use of it is that you can now plug this into the quadratic formula. So quick recap. Vertex form tells you the vertex, tells you which way the graph goes. That's useful. Standard form doesn't tell you where the vertex is. Does tell you where the y-intercept is, if that helps you for some reason. But it can be useful if you have to use a quadratic formula. My goal today is to try to show you how to convert between the two different formats. You guys would be able to solve this using the quadratic formula, right? Okay, well, we'll just leave it there. So here's, I just have a note here. The vertex is a very crucial point. If we were to have graphed this, this is what the quadratic would have looked like. And if we made it equal to 3, hopefully you guys can see there would have been 2 answers. But if we made it equal to 8, 8 is up here so high that there would have been no answer. The point I want to make is that vertex is a very crucial spot. If the vertex is too low, then the graph has no solutions. If the vertex is too high, well, now you get 2 answers. So we want to be able to work with vertex form. So here's kind of the main part of my lesson now. My goal is to help you guys work with 3 different forms of writing quadratics and be able to convert between all 3 forms depending on which is more useful. Okay. Standard form would be like 3x squared plus 7x plus 1. How is it useful? Well, you can use the quadratic formula. Formula. My goodness, I can't spell on this thing today. That says quadratic formula. It also tells you the y-intercept. Vertex form would be like minus 2x minus 1 squared plus 7. What's it useful for? Tell you the vertex. It'll tell you whether it's a smiley face or a frowny face. There is one more way that we've worked on writing quadratics at some point, and that's where you write it as like factors. So like, for example, if we had x plus 1, x minus 2, and write it like in a factored format of doing things. This use is finding the x-intercepts, by the way. What would the x-intercepts of this thing be if you had an x plus 1? Negative 1, yeah. And the other x-intercept would be positive 2. So, does this make sense so far? The idea that we can write quadratics in a lot of different methods. Each method has a different use to it. My goal now is to help you convert from one type of writing the quadratic to another. This is a really heavily algebraic-based unit. The idea being that maybe standard form is not useful for you. Maybe you'd rather have factored form, because then you can tell me what x-intercepts are. So let me try some examples here. What format is this in right here? Standard, factored, or vertex? So it's very useful for telling you where the vertex is. I know that it's minus 3, down 5, and it's opening smiley face. But let's say I don't want that form. Maybe that's not what's helpful. Maybe I'd rather know my y-intercept. Well, we could convert it into standard form like this. That x plus 3 is really written next to itself. So we could FOIL that x plus 3. If you FOIL it, you'd get x squared, 3x and 3x. I'm just going to put them together right away. Would give you 6x and 9. But I've left that 2 out front. So FOIL the 2 in. So you'd get 2x squared, you'd get 12x, you'd get 18, and then you'd minus 5. So in standard form, it's 2x squared plus 12x plus 13. What's that format useful for? Well, I know the y-intercept now. The y-intercept is 13. And if I had to use the quadratic formula, I could, if that was helpful. Does that make sense? What about trying to convert this guy to standard form? So currently, what form is this one in? Yeah, it's factored. So what use does this have? Well, I know where my x-intercepts are. The x-intercepts would have been at 1 and negative 2. So if that was helpful, that's what it tells me. The negative 2 still means it's upside down, by the way. But if I want to put this into standard form, then I should FOIL it out some more. So minus 2, and then I'm just going to FOIL the thing. So you get x squared minus x plus 2x minus 2. So it's minus 2x squared minus 2x plus 4. There, now it's in standard form. Is that too fast? I guess we'll follow that. So again, why would standard form be helpful? I know the y-intercept, plus 4. And if for some reason I needed to use the quadratic formula, I could now. To be honest, these first two things here, we already kind of did this back in our first unit to some degree, like the idea of being able to FOIL and factor and stuff. These are the ones that aren't overly, hopefully, too challenging yet. Let's try some more though. What format is this in? Okay, so my y-intercept is minus 21, and if I needed to, I could use the quadratic formula, if that was helpful. But maybe I could put it into factored form. Maybe that helps me find the x-intercepts. So what numbers add to give 10 times to give minus 21? Actually, that's not going to work. Let's make it plus 21. So that it can be x plus 3, x plus 7. Got a typo there. What's the coefficient out front of this thing right here? Just 1, yeah. So this is a smiley face graph, and the x-intercepts are at negative 3 because of the plus 3, and they're at negative 7 because of the plus 7. What about this one here? How do we factor one like this? Yeah, so we need to find something that adds to give 11 but multiplies to give first and last, which is 24. Any ideas? That'll do it. And then you cut this thing in half. And it gives you minus 2x. And you'd have x minus 4. And you'd factor out a 3. And that would give you, should give you x minus 4, shouldn't it? So then as a factored form, it's minus 2x plus 3 and x minus 4. Why is that useful? I know what my x-intercepts are. This intercept right here is going to be at 4. What about this one over here, the one with the 2x plus 3? Three over 2, actually. You have the right concept, you just flipped it around. And this one right now here means that x equals 4. How am I doing so far? Haven't lost you? Good, because that really was review. This is where it gets nasty. Going into standard form is fairly simple. You just FOIL stuff out. Going into factored form, also pretty simple. You just factor stuff out. Going into vertex form, however, is nasty. It's very difficult. So that's the point of my lesson here. We want to try to convert this into a vertex form. So what I'd like to do is I'd like to just do an example first. I found this sometimes works. Don't write anything down. Okay, let me show you how to do the example first, and then I'm going to erase it all and let me do it a second time where you write it down. Okay. In order to get something into vertex form, it needs to take this format: a x minus h all squared plus k. Our goal is to get it to that point. Okay. I have two main issues I have to deal with first. The first issue is I have to figure out what is my leading coefficient. What is my leading coefficient in this example right here? Okay, if it's 1, that's good news. It's going to make your lives a little bit easier. You would need to factor out whatever your leading coefficient is first. But since it's 1, we're actually good to start with. So I don't have to do that on this particular example. The second thing I have to do is I have to try to create myself something right here that can be written out twice. Because this really means you need x minus h next to a next x minus h. This thing right here is called like a perfect square. You guys ever heard that phrase before? Because it's written out twice. Okay. Let me give you some examples of perfect square trinomials. So just as a side note, if I give you x squared plus 10x plus 25, that is a perfect square trinomial because it goes back to x plus 5, x plus 5. And then the x plus 5 written twice really means you have x plus 5 squared. And so one of our goals is we have to try to write this as though it's a perfect square trinomial. Okay. In order to do that, what we do is we focus on just the first two terms and we ignore the last term. So you see how currently it is x squared plus 10x, and there's a plus 21. I'm going to write the plus 21 just way the heck over there. I'm not focused on it yet. Sorry, minus 21? Let's just go with it as plus 21 then. Sorry, thank you. What we need to do then is we need to put a number right here that is a constant, and that number has to be something that can create out of this little bit right here a perfect square trinomial. And really to do that, you need to focus on this number right here, the 10. You see how when we had 10x plus 25 here, we needed to use 5? Because what we need is numbers that add to give 10 and numbers that times to give 25. What we really need to do then is if 10 is the number that I'm given right here, you need half of 10. So half of 10 is 5. Does that make sense? But then I don't just add 5 right here. I have to add whatever that number is, 5. We have to square it. So I'm going to add 25 right here. And I made this thing now a perfect square trinomial. Here's the problem though. I just randomly added 25. Are you allowed to just randomly add numbers to equations? Not mathematically. Now, if this was an equation, like say over here, I could add 25 to the other side. But in a way, at this point right here, it's not really an equation. Maybe there's an equal sign way up there. But as a counter to adding 25 to the other side, what I could do is I could subtract 25 on the same side. Because if you add 25 right here and subtract 25 right here, see how you've kind of like made it equivalent? Because it cancels. Well, now what we have is two different halves to our equation. This little bit right here should be a perfect square trinomial because you made it that way. You should be able to write it as x plus 5, which really means you can write it as x plus 5 squared. We now know that the inside value for the x value is 5. To find the remaining number, it's whatever these two things becomes, which is minus 4. And this is now that exact same equation, but written in a vertex form. So my vertex would be at -5 and -4.
Where's the A then?
The A is just a 1 that's just kind of sitting out front the whole time. So in this example here, because there was a 1 as my leading coefficient on this one right here, I was allowed to skip that part. But we'll do an example where it's not 1. One more thought. Let me read through the next slide here, and then I'll come back and I'll do it one more time. So here are your steps. Step 1. If necessary, factor out the leading coefficient. In the example I just did, the leading coefficient was 1, so I didn't have to worry about it, but you might. Second step, you have to create a perfect square trinomial by adding and subtracting accordingly. So the rule for this is find your b value. Whatever your b value is, you have to find half of it, and then you have to square it. So we had 10. Cut 10 in half was 5. Square 5, it was 25. You're going to add and subtract 25. The first half of the thing should be a perfect square trinomial. The second half should be just two numbers that go together, and that's where your k value comes from. So let me try doing this one again one more time from scratch, then you guys can copy along if you want. So step 1, factor out a leading coefficient. If you wanted to, you could factor out a 1 and leave it as 1x squared plus 10x plus 21. But factoring out 1 is pretty bland. So, actually, I should be more specific. When you factor out the 1, you only factor out the 1 from the first two terms, actually. Because that minus 21 has to sit way over on the far side. We actually want to separate that 21 way over here. Okay, second step. We need to create inside this bracket right here a perfect square trinomial. So what we're going to do is we're going to add a number and we're going to subtract a number. And we have to find what that number is. So as a bit of like a side note here, to find this number, take 10, cut it in half, and then square it. The number you need is 25. And then you also want to subtract the 25. So then you've got your x squared, 10x, and 25. By design, this should be a perfect square trinomial. There should be a number that adds to give one number and multiplies to give the other number. In our example, it's 5. Because 5 and 5 adds to 10, and 5 and 5 multiplies to 25. So inside the bracket, you have x plus 5 squared. And then afterwards, you put these two numbers together, and it gives you minus 4. This is our equation. Our vertex then would be at minus 5, minus 4. Does that make sense? Okay, so in vertex form, this number right here, if you flip it to the opposite sign, it's your x coordinate of the vertex. And this number right here, you leave it exactly as it is. That's your y coordinate of the vertex. Let me show you how you can check your work. I think I've shown a few of you how to do this already. If you go to your calculator and go to your y equals screen, what you could do is plug in the equations you have and see whether they're the exact same. So I might plug in x squared plus 10x plus 21. That is the first equation. The other equation I had was supposed to be x plus 5 all squared minus 4. I believe these two equations are equivalent to each other. One of the ways you can test that, I've shown a few of you how you can make a graph line bolded. If you take the arrow and bring it all the way over to the edge, where there's that little like diagonal line, if you press enter once while on top of the diagonal line, it'll now make it like a thick line. If you then go like say zoom, I'm just gonna make sure it's a standard zoom. Have I shown you guys this? Zoom standard takes you to 10 by 10. So press zoom and then go down to 6. It'll just auto make it a nice 10 by 10 graph. What you should be able to watch is here's the first graph, and then here's the second graph right on top of it. Using the one was like a regular line, the other one was a dark line. What was that? Another thing you can check is go to your table of values. Have I shown you guys much on the table of values before? If you know where the table of values is, it's the second graph for table. You guys see how the y values for both the first graph and the second graph are the exact same all the way through? It means they're equivalent. So there's a way to check your work and make sure you did it right. That vertex then should be at -5 and -4. And if I go on either side of the vertex, hopefully you guys can see the symmetry now. The -4 is the lowest it gets. Then there's the 3s on each side, the 0s on each side, the 5s on each side. Any questions? Okay, let's try another example. So here's another one. It gets harder. Well, because I start you off with something fairly straightforward, right? But it does get harder.
Are we only ever going to convert a standard form into vertex? Like we want to.
Well, if I give you a vertex form to go back to a standard form, you just FOIL it.
No, I know. I would convert it into vertex form.
Oh, yeah, you can only convert from a standard form into vertex. So if you're given a factored form, you should then FOIL out the factored form to get to standard form, and then do this to get to vertex form. Okay, let's try another one. So this one's also fairly straightforward, based on the fact that the leading coefficient right here is 1. As soon as you don't make this a number 1, then it starts to suck. But for now, it's reasonable. So I'm going to factor out a 1. I'm going to leave you with x squared minus 4x. And then way the heck over here, I'm throwing a minus 11. We now need to make a perfect square trinomial out of x squared minus 4x. So what is half of minus 4? And then we're going to re-square that. Okay, so what we're going to do is we're going to rewrite what was here. We're going to add 4. And then way out here, we're going to have to subtract 4. Because I can't just randomly add 4 for no reason. I have to subtract it out here. Walker, can you close the door? Okay. The outside numbers you can probably combine right away if you want. It's going to be a minus 15. We need now to figure out what number adds to give minus 4 and multiplies to give 4. Yeah, it should work out to be whatever the number was before you squared it. So like whatever half of this middle number here is your number. So that'll be x minus 2. Technically it's x minus 2 next to another x minus 2. But if you don't want to write this step, you could skip this step and just go right to leading coefficient of 1. X minus 2 is being squared and minus 15. Why is this format useful? I know where my vertex is. 2 minus 15 is my vertex.
Should we write it like y equals, or is that really?
Yeah, we probably should have been writing it as y equals, I guess. I mean, if you didn't, I don't think I'd take a mark off. Because like you'd have to make it y equals to make it go into an equation format. Okay. So far?
Yeah.
All right. Here's where it sucks. Okay, so here's the first problem. We need to still account for leading coefficients. This guy has a leading coefficient of 2. That means the graph is going to be slightly squished in comparatively. It's still going smiley face, not frowny face. We have to account for that too. So the last 2 times I've been going through the motions of factoring out the number 1. This time I have to factor out the number 2. But only, yes, only from the first 2 terms. So write that minus 3 way the heck over there because you don't want to accidentally have it be part of this first half of the graph. And factor 2 out of these first 2 terms. Not 2x, but just the 2. So if you factor out 2, you're left with x squared plus 4x. Okay so far? Okay. We now need to try to find a number to add right here. By the way, this number here will always be positive. Why will this number here always have to be positive? Yeah, because to find that number, you're taking half of a number and squaring it. So I guarantee you it's a positive number, which means that outside here, you're probably subtracting a number. So you have to add a number right here. and subtract the same number right here. Actually, that's a lie. Okay, what number needs to go here? 4 is correct. Because half of 4 is 2. 3 squared again is 4. Here's the most common mistake kids make. They put 4 right here. And that's not right. It's supposed to be 8. Okay, so here's the logic behind that. You put a 4 right here. But you didn't actually put a 4 right here. It looks like a 4. But this 2 right here would have times by that 4 to make it actually 8 that shows up there. It appears as though you only put 4 there. You actually put 8. So therefore you have to subtract 8 based on that 2 sitting right there. If kids screw that up, that's the most common mistake they make, is they just put a plus 4 and a minus 4 right here. So you have minus 11 afterwards, because that's what 8 minus 3 is. 2 is your leading coefficient, and you should then have something written squared. What perfect square does this thing turn into? X plus 2, because 2 plus 2 equals 4, and 2 times 2 equals 4. So I now have an equation. It's still going upright, but it's a little thinner than it would have been. The vertex is then at minus 2, minus 11. Yeah. Of course, there's more. How many more slides do you have? Oh. Okay, this is like the creme de la creme. Like, if you can solve this question here, you know what you're doing. Because this one has 2 problems. There is a leading coefficient out front, which you have to factor out, but it's the second number that buggers things up. 3 and 7 do not divide nicely. And that is one of the biggest issues you'll have. I will rarely ask you to do this, but I will ask you occasionally. So just so you guys are aware, like, this is not going to be every single time, but it could happen that there is not only a leading coefficient, but 3 and 7 do not fit nicely together. That's what makes this one the most challenging. So, let's give her a try. I'm going to write that minus 1 way the heck over on the far side, because it's just not what I need to start with. We need to factor out the minus 3. The minus 3, which makes the graph go thin and upside down. So minus 3 can come over here. When I factor minus 3 out of minus 3x squared, you just get x squared. It's that second number that's more challenging.
Do you want to do the decimal or a fraction?
It's a fraction. Yeah. It's going to be this. It's going to be minus 7 over 3x.
Can't you factor the itself?
We can, but we don't want to. You're right. If we were just doing a common factor, we could factor the x out, but we're choosing not to. Okay, let me try to explain how I get 7 over 3 here. If you do minus 3 and minus 7 over 3, do you guys see how, like, if you foiled this, these guys would cancel?
Yeah.
You get the 7 there? Long story short, whatever this first number is right here, it's going to be divided by this second number here.
Yeah.
Okay, now for the challenging part. We need to figure out a number that we need to add right here, and that we need to subtract right here. And the ugly part about this is now it's not going to be a whole number. It's going to be a fraction. So first we got to figure out what half of this value right here is. This minus 7 over 3. What is half of it? Don't use your calculators. There's an easier way. It's minus 7 over 6. Because half basically means make the bottom number twice as big. So like you can use your calculator, I guess, and do 7 over 3 divided by 2, remake it a fraction. Or if you understand this concept, if it's 7 over 3, just take the 3 and make it twice as big. You used to have 7/3. Now you have 7/6. That's all. Because like a 1/6 is smaller than a 1/3, right? Then you have to square that number again, try to avoid using your calculator because it might just throw you off. 7 squared is 49, and 6 squared is 36. And I guarantee you that this number right here is going to be positive. Okay, now we have to subtract a number outside here. However, now I might suggest, now is the right time for using the calculator here. That number right here, though, has to get times by -3. And when I like to show it, I put the subtract right here, and then I do like -3 times 49 over 36. So you know how we were adding 49 over 36 right here? I have to subtract 49 over 36, except there's that -3 out front.
Oh, I forgot you had to times it again.
So that really common mistake, you have to times by minus. So this bit right here, you use your calculator for that bit if you want, okay? So what you need is a negative 3 times 49 over 36 minus 1. I got 37 over 12. So make sure you do a negative, then bracket -3, 49 over 36, and then subtract 1. And then fractionize it. That's a verb. Adjective? Verb. It's actually. Anybody else able to get that?
I got 37 over 12. I don't see what.
Yeah, I get
I got 37.
Even one bracket here.
One bracket is better. Because what's happening is you open the bracket here, you open the bracket here, you only close the single bracket, you just close the second one.
Then fractionalize that. Fractionalize. Any other issues with that section? Okay, now for the perfect square trinomial. This thing right here is a perfect square trinomial, only it's ugly because there's fractions everywhere. That being said, if you took my advice and chose not to just rely on your calculator, it's based on this bit right here. Okay, you still have the -3 out front. You're still going to do something squared. But numbers that square to give 49 over 36 are 7 over 6. And whatever half of 7 over 3 was is also 7 over 6. So I actually prefer if on this section here you try to avoid using your calculator, because it'll be -7 over 6. Whatever this number was right here when you cut it in half.
So when you have fractions like that, it's always that first.
So whatever this number is right here that becomes the fraction, take that and just make the bottom number twice as big. So if it was 7 over 3, make it 7 over 6.
And that's just your.
And that's what'll go right here.
And keep it.
And well, because this one was negative, keep it negative. But if it was positive, then it'd be positive. Okay. Regardless, the number that you put here is going to be positive, I guarantee it. Because if it was a negative, when you square it, it becomes positive. So all of that tells us the vertex is at 7 over 6, comma 37 over 12. Whatever those are as decimal numbers. If you can do that, you can do pretty much anything. I'm done. Okay, let me try doing one more. What's my last slide? Just a summary?
No, there's a question.
How about this? Why don't you guys take 5 and then we'll do the question after a break. Let's do that. We'll take a break now. Okay, let's try one last example here. Before I do that, typically I don't just ask you questions like this. Normally this is going to come up as part of like a larger word problem. I didn't actually have a word problem to go along with it, but let's just pretend that this is like the diving board kind of question again. What you could do right off the bat is just graph this thing. So I'm just going to go over here, y equals clear, minus 3x squared minus 18x plus 10. Actually, no, I'm going to just do it on a regular graph just to start to see where it shows up at. Yeah. Okay. I mean, maybe this doesn't really fit the diving board question quite as well. But ultimately, what I'm asking you to do is figure out where it equals 3. How many answers should I expect? I'd say 2, right? In a word problem, I'd say that the answer way over here in the negatives, that's probably extraneous. Because you really probably shouldn't have like a negative time or distance or something like that. Chances are what we would want is this answer right here. And I don't know, I guess this would be where the guy is on his way back down, I guess. Where is he 3 meters above the water? I know it's not perfect. What you could do then is second calculate intersect. And intersect should be able to find you where they cross. I got 0.3665. Okay, well that's where the other one is, possibly.
I got
And then did you get 3 for one?
I got 6.366. Anybody get what I got there?
Yeah.
You did.
I just got 0.6 or 0.36. I didn't get the 6.36.
Did you solve for the other one though? Did you actually go and?
No, I just.
Okay, so you just did it one at a time, right? Because like you just solved for this one. Next time you have to move your cursor closer to over here so it finds the other one. It's not working?
So second calculate intersect. Just press it 3 times basically. Did you only press it twice? No. You want to do it again. Second calculate intersect. 1, 2, 3 times there. There's the other one.
Okay, is everybody able to get those 2 answers for x? Okay, my goal now is to try to find those values for x, but not use our calculator. We're going to confirm it using either the quadratic formula or by what we just learned completing the square. So let's try the quadratic formula first. You're going to take minus 3x squared minus 18x plus 10, and you want to see where it equals 3. How do I use the quadratic formula now? That'll work. Because we have to make it equal to 0. To be honest, I actually don't like using negative leading coefficients myself very much. So I could kind of flip all the signs and make it positive 3x squared, positive 18x, and minus 7. I'm just flipping all the signs around just because I don't like using negative leading coefficients. So, negative 18 plus or minus the square root of 18 squared minus 4, 3, minus 7, all over 2 times 3. This is what I got. Let me know if you get something different. You guys get that?
Yeah.
Normally I'd say leave that there, but let's just confirm that this equals a decimal number that's the same as what we just got. So if I do minus 18 plus the square root of 408, and then divide by 6. I got 0.3665 and minus 18 minus the square root of 408 divided by 6 gave me negative 6.3665. Does that make sense? Okay, you may need a sheet of paper for this last one if there's not some left over here. Is there like a spot for one more left? Okay, because now what we're going to try to do is, by the way, this is completely not purposeful. Like, if you had to solve for what x was, you would either use your graphing calculator or you would probably do the quadratic formula. But what we could do, just because we really love math, is we could complete the square, and then we could solve it once we complete the square, which is a lot of unnecessary work, but it's possible. So I may ask you to do this once in a while just to prove that you have good algebra skills. So, sorry. So let's try completing the square. It's minus 3x squared minus 18x, and I'm going to throw that plus 10 way the heck over here. Okay, completing the square. Step 1, factor out any leading coefficients. We have a negative 3. So I'm going to factor out the negative 3. It's going to leave me with x squared. Fortunately for us, 18 does divide by 3, and it makes it plus 6x. Let's start. Then we need to make a perfect square trinomial out of the 6. So we need to add a number and then subtract that number later. So half of 6 is 3. Square root is 9, so we need to add 9. On the outside, though, we're going to subtract negative 3 times 9. If you're going to make a mistake, I'm going to say 9 times out of 10. It's you forget this little minus 3 right here. Because of the fact that there's a minus 3 out front. You didn't actually just put 9 right here. You did minus 3 times 9. That'll work, yeah. So 27 and 10 actually gives you a 37 by the time you're done. Yeah. You have a minus 3 right here, and this will be x plus 3 all squared. So this helps you complete the square. We now know where our vertex is. This is also possible to solve. What was this supposed to equal? It was supposed to equal 3, was it not? So now if I take all of this and I make it equal 3, I can actually solve for x. In order to solve for x, I'm going to have to take the following steps. I'm going to have to subtract 37. I'm going to have to divide by minus 3. I'm going to have to square root and then subtract 3. So I'll do it in pieces though. Subtract 37 from both sides. 3 minus 37 is going to be minus 34. It's going to give you a fraction. Just leave it as a fraction. 2 negatives divided by each other gives you a positive. So just leave it as a 34 over 3. And then how do you get rid of the squared sign? Square root both sides. So that's what this is going to do. By the way, when you square root both sides, though, you have to take the plus and minus square root of both sides. Because like when you square roots can sometimes be positive or negatives when you square root. So don't forget to throw that plus or minus part in there. And then last step, subtract 3. So your answer for x is the plus and minus square root of 34 over 3. Subtract 3. That's what x should be. If we did it correctly, it should be those same decimal numbers that we just solved earlier. So let me double check then. So do like the square root of, does that make sense? Do the square root of 34 divided by 3, and then subtract 3. So I got 0.3665. And then just type in like a little negative sign in front. Not the big negative sign, but the little negative sign. Square root of 34 over 3 minus 3. And negative 6.3665. This is sometimes preferable because it's an exact value. That being said, if we don't care about rounding, which normally in this section I don't, I'm okay if you're able to find these numbers right here. Most of what we just did there is an exercise in just being able to practice our algebra skills. Not because it's the most efficient way of solving a problem, but just because, I don't know, sometimes I need you guys to practice algebra skills. So, that makes sense? So 3 ways of solving this problem. You could put it into your graphing calculator, find where it crosses. It's going to cross twice probably. Well, those are your 2 answers if you can intersect. That's probably the fastest way of doing it. If I ask you to use the quadratic formula, hopefully you're able to use the quadratic formula as well. This third method, I'll ask you once in a while just to make sure you know how to complete the square. So the far number way over there, factor out the minus 3, find your perfect square. But don't forget when you're subtracting that number to account for the leading coefficient again. Once you get your vertex form, make it equal to 3, because that's what we were looking for when it solves. Subtract, divide, square root. When you square root, don't forget you have to square root for a positive and a negative, and then subtract this last number, and you should get the same answers again. Often what I'm going to do in a question is I'm going to ask you to solve for the intersection points, and then I'm going to ask you to do it 3 different ways. Once using a graph, once with the quadratic formula, once with completing the square. The good news is that you'll know whether you did it right because you get the same answers all the time. On one of my tests, I think I actually tell you what the answers are, actually. I even tell you what the 2 answers are supposed to be, and I say, show me how to get these answers more than one different way. Yeah, Devin. Yeah, for sure. How far should I go back up? Okay. Okay, questions? Wait, completing the square, I mean, it's very formulaic, you do the same thing, but it is challenging if the complete the square values are not nice. Like if the first coefficient is a 3 and the next one's a 6, that's perfect, you can deal with that. But if the first one's a 3 and the next one's a 7, then you've got fractions. And that's probably the one that sucks. So, by the way, if you want practice on completing the square, make up your own equation. You don't need me to make one up for you. If you want to make up something nice, make it like y equals 2x squared plus 8x plus 1, because 2 and 8 go nicely together. But if you want a real challenge, just make it 2x squared plus 9x plus 1, because 2 and 9 don't go together. So you can just make your own examples up for practice. There is